Hello, everyone. I have the opportunity today to talk about the future of Ethernet, which I've been very active with for the past 20 years. We'll be looking 20 years out into the future, what Ethernet is going to evolve to. In order to do that, we really need to look at where we came from and where Ethernet is today. In order to see the progression and understand where things are going, and as well as the connectivity. It's all connected. The Ethernet is actually designed for the optical connectivity. The future of Ethernet is not really defined yet. We're in the process of defining really what's going to happen for the next 10 years and projecting for the next 20 years. Before we do that, I think we really need to start discussing the very basics of Ethernet for those on the call that are not familiar with Ethernet. So Ethernet today was actually developed in the late 1970s, early 1980s. All telecommunications that exist today is basically built on what we call the open system interconnect model. This is an ISO standard that defines 7 layers for all data communications. The top 4 layers, the application, the presentation, the session, and the transport layer are all done in software today. The software then forms frames. The data is put inside a payload, as a payload, and it's passed along to hardware. The hardware is the network layer in this model, and it's what creates the Internet protocol that is going to be traveling through the network. The next layer down is the layer that most people are familiar with, the data link layer. This is where you give MAC addresses. The MAC is the media access controller, and it communicates with whatever physical layer is under it. For example, it could be Ethernet, which is what we're going to be talking about here, but it could also be Wi-Fi and other types of interconnections. The data link layer puts in the MAC address and takes the TCP/IP layer and transmits that down to the physical layer, which is, in this case, we're going to be talking about Ethernet. Ethernet is a point-to-point connection, interconnection. The first octets, 8 octets, are nothing more than ones and zeros to tell the destination that it's an Ethernet frame coming. And embedded in the payload is communications that Ethernet embeds into the data in order for Ethernet to be able to handle the interconnection. Looking a little bit closer at the physical layer, which is typically an ASIC, an application-specific integrated circuit, there's a reconciliation layer which does all the communications between the physical layer and the MAC, and the PHY is made up of several different components, as well as what we call the PMD, which is pretty much the transceiver. And what Ethernet defines is the media-dependent interface. It's how, if it's optical, it'll be the average power that you need to come out, the data rate. If it's copper, it'll send data out through different lanes or different copper pairs. So let's now look at the evolution of Ethernet. Although Ethernet was developed in the very late 1970s, early 1980s, it really didn't become very popular. It was still being explored, trying to understand how to use it. They had competitive types of network technologies, but there was a very significant effort in trying to get Ethernet specified as the international standard for all data communications. What really started optical communications over Ethernet was the invention, and I shouldn't say invention, the development of 10 gigabit VCSELs. VCSELs are vertical cavity surface emitting lasers. Those are multimode lasers, as opposed to single mode lasers, which are quite expensive. Those are planar devices, the edge emitters. They're very expensive distributed feedback lasers. So single mode fiber is always going to be cheaper, more expensive, sorry, than multi-mode. And most of this talk will be on the multi-mode PMDs, that is transceivers, and the technology that goes behind them. In terms of single mode is really for long-distance communication. The minimum reach, which is only recently specified for single mode, is 500 meters, and those are at very high data rates. But typically, for single mode, we're really talking about 2 kilometers, 10 kilometers, 40 kilometers, or 80 kilometers. So these are long-distance optical communications. In data centers, you really want to stay with multimode. And what I like to show today is that multimode has a long life. So in 2002, the first real standard, optical standard, was ratified. That was 10 gig base SR. The 10G is the data rate, the first few numbers in that nomenclature that the IEEE uses. That's the data rate. The base just means baseband. The S means short wavelength, and the R, many people think it means reach, but it's not. It actually stands for 64, 66-bit encoding. It's a type of encoding that Ethernet embeds in these Ethernet frames. It also, this was a big step. Not only was the first real high-speed VCSELs developed, but a new fiber type was invented, which was called OM3. It's an optical multimode 3. It's a laser-optimized fiber. What this means is that the refractive index profile, the design of the fiber, was specifically made for the VCSELs to optimize the bandwidth. However, 10 gig Ethernet actually was not really deployed widely for about another 8 years. During that time, what we did in research here at Panduit is we started looking at the actual data communications at 10 gig over our own 3 fiber. And much to our surprise, what we discovered is that the bandwidth of the fiber didn't correlate to the actual channel performance. This was a big surprise to us because there was a lot of research and modeling that was done for this standard. No one could understand why this correlation was very poor. What we discovered years later, because we came to the conclusion that they can't be measuring bandwidth accurately. So we built our own measurement system. It's called differential mode delay measurements. And we measure out the bandwidth directly. And what we discovered is that for VCSELs, there's a correlation between different dispersion penalties in the fiber. And this was overlooked by the technical community. As a result of this, we actually invented a new type of fiber, which is a dispersion compensating fiber, which it takes the 2 different dispersion penalties, and we adjust the fiber to let one dispersion penalty offset the other. And from this, we actually invented what we call signature core fiber, which is a dispersion compensating fiber, and you get about 20% higher bandwidth using this type of fiber. We went public with this. The industry wanted a similar type of fiber, so Panduit chaired the development of an OM5 fiber, which is essentially a commercial version of signature core. There are some big differences between the fiber. We did have a lot of patents on this type of technology, so OM5 is not quite as good as signature core, but it's close. So once 10 gigabit really started taking off, the standards body decided to go to next generation. And if you were to look at the evolution of Ethernet, you'd see it was the very first one was 2.9 megabits per second. So we're not going to really look at that. That was done in the very early 80s. But 1 gigabit or 1,000 megabit, there was a popular first introduction of Ethernet as we know it today, but it was hardly used because the copper was able to provide that connectivity. In terms of 10 gig, the copper can go about 100 meters, but there were applications where you needed more than 100 gig, more than 100 meters, so 10 gig really started to take off. And the 100 gig was really the next logical step, and this particular standard was like no other. It actually took us a year and a half of arguments to decide whether it should be 100 gig or 40 gig. The server makers wanted 40 gigabits, but the IEEE wanted 100 gig because we usually increase by orders of magnitude. In the end, both solutions were adopted. However, the 10 gig Ethernet required what we call parallel optics. So does the 40 gig. In order to go beyond 10 gig, we had to invent a new way of doing that. And what we did is we started putting in pairs of fibers, each pair to carry 10 gigabits per second. So 40 gig SR4 means it's 40 gig with four, it has the same, it's short wavelength, it's the same coding scheme as what was previously done, but it's 4 fiber pairs. And Panduit actually had OM4 adopted as a media type option for that standard. Much to our surprise, there was no one foreseen this, but customers started using 40 gig as what we call breakout. Because we use parallel optics, it turns out that each of these 4 lanes of 10 gig can actually be separated and function totally independent from each other. And this is called breakout. The advantage is, I will actually show you what the advantage is in a few slides from now, but you can get a higher port density on your switches or routers. You can have a 40 gig port, plug in a 40 gig transceiver, and you can break out each 10 gig into to a separate transceiver. During or at the end of this standard, 25 gig transceivers were now developed, and those were actually developed on a different material system. As soon as we had 25 gig VCSELs, we had a call for interest, and we started developing a standard for 100 gig SR4. So this would be 4 lanes of 25 gig. And what the advantage of this is you can use less fibers in your connectivity. Instead of going with 10 fiber pairs for the previous version, SR10, where you need a 24 fiber MPO connector, you can go to a standard 12 fiber MPO connector and only use 8 of those fibers to communicate 100 gig. So that replaced the previous version, and at the same time, as this thing was being evolved, we started another standard for 25 gig SR so that you can now break out the 100 gig. Shortly after that, Panduit is actually the first company to demonstrate 50 gig using a new modulation scheme. So VCSELs today cannot really operate faster than 25 gigabits per second. Now, there's something called symbol rate and bit rate. Symbol rate means, in this case, if you're sending out data, NRZ, which is non-return to zero, this is binary data. These are symbols, and each symbol happens to be a bit. But for 25 gig, you can't drive the VCSELs any faster. So the symbol rate, what we do is we change the modulation scheme from non-return to zero to PAM4, pulse amplitude modulation, which are more optical power levels, which allow us to double the bit rate given the same symbol rate of just a 25 gig VCSEL. So it was a way of getting a higher data rate without really changing the design of the VCSEL. And with that, we started developing new standards, which is 200 gig SR4 and breaking it out to 50 gig SR. Now, it turned out at this point, OM5 was now standardized. and the fiber manufacturers wanted to sell OM5. So during the writing of this standard, they decided to make a proposal for 100 gig SR 1.4. The second, that dot and a 4 means the number of wavelengths. We started looking at this, and we realized that this solution really wasn't best for the customers. So we at that point proposed the 100 gig SR2, which was adopted, and that went on to the next generation of 400 gig MAC rates and the development of 400 gig SR8. Once again, the same group wanted to get another standard developed for wavelengths. That motion also failed, which led to the development of 400 gig SR 4.2. That's 2 wavelengths. So that's where we are today. Looking forward, we're currently writing the standards for 400 gig, 200 gig, and 100 gig using 100 gig lanes or VCSELs. These are a little bit faster VCSELs, and it's also pulse amplitude modulation, so we can get these data rates. And once again, Panduit was the first to demonstrate feasibility. We're now in a study group talking about 800 gigabits per second, and 800 gig was in fact adopted as an objective, so we will be developing an 800 gig. And there's discussion now for including that standard 1.6 terabits per second. My guess it will go through, it will be adopted, and at that point we'll be making a presentation to the IEEE to adopt the next generation of Ethernet, which will be 800 gigabit as well as 1.6 terabyte. Going beyond 800 gig or 1.6 terabyte is going to be extremely difficult. We're going to have to add more wavelengths, which could have a problem with eye safety, but there's always the opportunity to go into low-cost single mode in the future, and we're talking really 10 to 20 years out. In terms of connectivity, most of the links that are out there are in fact less than 100 meters. This is data I presented at the IEEE showing. So multimode fiber can support most of the channels that are out there, and the application for multimode will in fact be switch to server. That will be the primary. It's going to start replacing copper in the 50 gig and beyond. The ASICs that are in the switches have very large port counts. In this case, this is state of the art. The ASICs have 256 50 gig ports. That's a big switch, but by ganging 8 of them together, you can go out on a 400 gig port. So you reduce the number of ports from 256 down to 32, a 1RU32 switch, and then you break it out. Because you could access so many servers with one small 1RU switch, it requires longer connectivity, and that's why copper can't be used for these higher data rates. And multimode fiber will be used primarily for all breakout to support these lineups of servers. Next slide. So looking out really 20 years, this is the evolution of the data rates and the technologies. We'll be seeing 200 gig PAM4 in about, well, the way it works is when a standard is developed, it takes about 3 to 5 years before it's actually deployed in volume. So if you look at the 200 gig, which people are discussing now, it really won't start the development of that standard for about another 3 to 4 years from now. It'll take about 4 years to write the standard, and then about another 4 to 5 years after that for it to be adopted. So if you look at this chart, what I just showed will really be the technology that will be deploying over the next 20 years. And with that, I'll take any questions.
I don't see any questions coming in. I'll just ask one here that just came in. Will there be, multimode fiber solutions for 200 gigabits per second per wavelength?
Yeah, so the question again, will multimode VCSELs be developed for 200 gig multimode? And that's doubtful. What limits the bandwidth of lasers is its physical size. The larger the device, the more capacitance it has, the more parasitics it has. And when it has capacitance, there's a limit to how fast you can drive it. It's like charging a capacitor. So VCSELs are inherently larger than single-mode lasers. Single-mode lasers are about 8/10 of a micron high and about 8 microns wide. It's a strip. And that's very, very tiny, so they have very high rise times, very little parasitics. Whereas VCSELs are made to have a large, wide emitted signal and inherently has a high capacitance. So I doubt very much whether there'll ever be a VCSEL that can drive very, very high data rates. It'll be single mode at that point. There are other technologies that theoretically can be developed, but no one's even discussing anything like that.
Okay, I don't see any other questions coming in, so thank you very much, Dr. Pimpinella.